nor do we even really truly understand the kind of features it's selecting from that all the time. Okay, that goes back to whenever you're looking at your CNN and you're looking at the kernels, you're looking at the output of the kernels, you're trying to understand what it sees from that space. It's not always a directly intelligible or directly visually inferenceable understanding of what's going on in that space, okay? I know I haven't come up with a video. I'm still going to come up with a video, but you guys want to talk through some of the topics for the exam? Is that preferable today? I'm noticing everybody is like straight spaced out. I don't know if I'm boring you guys with talking about transfer learning, but I'm assuming you're probably in the same space that most of my classes are, one class before an exam, and that is talk about the things we need to know rather than the things that we are going to have to know after the thing that we have to do now, okay? I better come out for this because people are going to be mad. I could be a jerk and not, but I'm going to like that. You gonna let me? Okay, they're good. I think I have to do this one. Okay. Performance evaluation. We actually just talked during the last lecture about the reason why performance evaluation is such a necessary component of machine learning frameworks, right? We said you've got to figure out what your goal is, and you have to figure out how to determine the distance away that your guess was from the goal. This is the baseline understanding of stochastic methodologies in the effect of saying, when you have a very, very large space to search, there's not always a appropriate methodological search to implement in order to be able to come up with an ideal set of solutions, right? The algorithmic process of adjusting every feature iteratively every single time in order to find the exact right outputs is going to take too long. Anybody experience that with the last assignment? Mm-hmm. Yes, you did. If you try to approach it from a strictly fully every grid search process, it's going to take an inordinate amount of time, all right? So what we want to do, oftentimes we want to apply the same techniques that we're utilizing at the micro scale with regard to the gradient adjustment. We want to provide those at the macro scale. Take relatively large steps, look, see how the system is improving, right? And then as you're getting closer to what might be a goal in your space, or as your improvement continues, do what? Slow down maybe a little bit, take smaller steps and guess how they're coming as you get further and closer to a set of parameters that might seem more ideal. You're going to have to use some intuition, all right? But you're also going to be able to utilize some of these performance metrics and the change in those performance metrics to be able to understand what's going on. Think about it this way, if you wanted to categorize mean squared error with respect to the improvement of model performance, you could look at the slope, right, the instantaneous change in model performance as you adjusted the parameters, which is like the number of nodes or the learning rate of that model. You could also, if you continue to do so in a meaningful and procedural way, look and see how the model's performance is directly affected as a higher order, right, a meta analysis, hyper-parameter analysis of the system. The reason why I say that performance metrics and sort of understanding the goal of a performance metric is a key factor for our utility here is that at the end of every fully connected network, there is going to be some form of error assessment. The two that are predominant are going to be mean squared error for something like regression analysis, and the second one, which is cross correlation, right? Cross correlation, we looked at the equation for it, okay? It's a chunk of an equation. I'm more interested in having you guys understand that it is a logarithmic analysis, right? It looks for likelihood assessments. So it says how likely, with respect to the probability of several different possible spaces of this sample being in, right? Which is the probability that is the greatest for this particular sample. So cross correlation is going to take into consideration how well that log likelihood-based assessment system is doing at placing samples in their appropriate classes. If we utilize a strict binary, you got it all right or got it all wrong system, it makes it really hard for us to effectively back propagate through that network, right? Because each individual output, if you think about it from the perspective of just using just accuracy as the method for propping back the gradient of a 10D output network, right? Like the one that we've worked with MNIST and Fashion NIST, and you try to prop that back just on accuracy or sort of some kind of MSE type error for one-dimensional output, it would be very off because you're going to need to have all of the relevant probability estimates for all 10 classes to determine how the error for the previous layers needs to be adjusted, okay? We don't want to do that by hand, okay? Matter of fact, you guys probably never want to touch another hand calculation again, but that's what I'm doing. I'm going to show you how to do a couple hand calculations again, just so that you can notice the key elements, okay? But we're usually talking about cross-correlation with respect to a specific layer and a specific methodology that we utilize for fully connected layers, and that is called the softmax functionality. You need to understand it at the level of what it's employing, and it probably wouldn't be a really bad idea to sort of understand the softmax function, you know, from an equational standpoint, right? We looked at it briefly, but I would say being able to explain what it does, right, is probably enough, all right? So I think in a sense, if you know you can look it up, right, that's always been my case. You know you can look it up, you don't need to, you know, figure out how to memorize it, okay? I want to mention something now, actually. I've reconsidered my position on note sheets. I will allow you, and this is explicit so everybody understands this, I will allow you one single-sided A4 page, handwritten in your handwriting. You construct it yourself, okay? It's your note sheet, you own it. Because I'll be honest with you, it's probably not going to do you any good unless it's the one you make yourself. Put out the effort to write your own. You can look at formulas. You can look at basic definitions of frameworks. And you can do descriptions of network characteristics, okay? Do not rely on that too heavily, because I don't want you to just write wholesale definitions to answers to questions on the exam. This causes problems. Because if everybody looks up the same definition, writes the same definition on their note sheet, and then copies that same definition to their exam paper, now we have a problem, because I don't know what went wrong where, okay? I know in some spaces, and probably for a lot of your academic backgrounds, coming up through the programs you've been in, memorizing and knowing exact definition, knowing exact information about some specific topic has been incentivized. It's been ingrained into you to be the primary thing of interest. My goal is not that, okay? I don't want you to be able to recite to me the definition by rote. I want you to be able to put it in context of how it is used. So some of the questions you guys are going to be dealing with are going to be scenario driven, right? Your network starts to overfit with a specific kind of data, right? You're going to have to think about how that impacts the process and answer me what might be happening there. Don't panic about that, right? Because my relationship to this process is, if what you provide for me makes a degree of sense, and you're able to use the terminology appropriately, and there's some logic involved with it, then that is an acceptable answer, right? It's a direction you can go in. As I said beforehand, one note sheet, okay? You're going to write your student ID on it, you're going to write your name on it, and it's going to come in with your exam, all right? If you have anything else on your desk, it goes away, okay? And it is one-sided, and I originally was thinking maybe I would get those approved by TAs, but I think what I'm going to do is I'm just going to have that happening on the day of the exam, okay? So as you come in, You're gonna walk through the door, you're gonna have it looked at, and you're gonna go to your seats, okay? Yes?
Will an equation sheet still be provided?
I'm gonna still provide you with a basic equation sheet that should have like most of the stuff you'll need for it. I already have it made up, so I'm gonna tack that on the back, okay? So this is mainly for you to have some, kind of crib framework notes. Make sure you're writing it in your own words as you're putting it on the sheet, and that'll make sure that you don't have to worry about trying to transliterate it into some other sense if you decide to use that reference in place, okay? And don't just use ChatGPT. Make sure no, that's not a joke. Make sure you're utilizing confirmed, validated sources like textbooks or websites that are linked to text sources, because ChatGPT will straight up lie to you, and oftentimes it will give you an emphasis on things that are not correlated with things we've discussed. I will definitely be able to tell whether or not you've been in alignment with the things we've been discussing in class if you start using terminologies and metrics that don't apply to those things that we've discussed, okay? There's a reason why I want you to focus on being engaged in this process, and that is you can't necessarily get all of what I'm trying to bring to the table here if you're just using some random generator to get information, okay? Confusion matrix and interpretations of the confusion matrix as a methodology for assessment of a model, right? That's a really good tool to have under your belt. Okay, everybody remember that the confusion matrix is an output for classification style problems. Anybody use a confusion mat to determine what the performance was like for your fashion and mist? You did? Okay,
I did.
Good. Nobody else tried that? Nobody else threw that at it? You did? Okay. I thought about having that included within the space. It's a little chunky because it's a 10 by 10 matrix,
yeah, huge.
right?
Mm-hmm.
But if you throw something like a coloration mechanism onto it that you can do with like Matplot, it does make it a little bit more intelligible. We looked at one or two of those in the code that was embedded in the samples I put forward for the classifier output. When you get up into hundreds or thousands of samples, there's absolutely no purpose in interpreting those. They're not possible. But at lower dimensionality, if you're just looking at generalized positive, negative for binary classification or something like 10 or 50 classes, they still have a degree of utility in being able to interpret what's going on with the system. All right. Modeling in general and the characteristics of complexity and the risks of overfitting. These did not disappear with neural networks. Matter of fact, they got much more problematic. Why? With respect to the types of parameterization that we had for simple linear regression, right? We may have had one or two parameters, right? Mm-hmm. A simple linearity is what? Slope and a bias, okay? Mx plus b. So it doesn't take very long for us to be able to figure out how much more difficult it becomes whenever you have two elements in the hidden and two elements in the output, right? That's automatically, parametrically, much more intense than what we've used previously for regression analysis. So why am I talking about that? Because it's such an obvious thing. Encourage yourself to think about the notion of adding nodes to a network as a process of a geometric expansion in the level of complexity, right? One node added to a layer has both the dimensionality of the input, right, and the dimensionality of the output, number of weights that get added to that network. So if you have a high dimensional input space, right, you have a large layer behind it, and you have a relatively large layer in front of whatever the hidden node that you're making incremental changes to, you are making large strides when you're changing the number of nodes by what? 5 or 10 nodes per time. Those are huge changes in the outputs. So complexity and overfitting and the things that we do to attempt to avoid overfitting, especially in neural networks, right? We've talked about a couple of those things. Normalization, batch processing. We've also talked about the idea of early stopping, okay? But we've also talked about the idea that understanding your data and being able to make some useful interpretations of what's going on with it internally is as important to parameter selection as anything else. So use some intuition and do some basic hypothesis type testing and be able to give you a better outcome in that space. MLPs, multivariate systems, and the decision surfaces they create are effectively the mechanism by which we utilize neural networks to approximate functions. All right, so the universal function approximator notion, that is, at any reasonable degree of error, that a neural network exists that can produce a functional approximation relative to that non-zero error, okay? Weight indexing systems, I know we had a problem with this on one of the keys that I put in place. I'm gonna ask you guys to either transfer a set of matrix notations or to label the nodes on a network. I don't care what sort of system or operation you use as long as it makes a reasonable amount of sense, okay? So you're gonna have both the network and the matrix that refers to the network. So as long as you put the same notation on the diagram and in the matrix, right, that is fine. This is not gonna be a stupid complex network. It's gonna be a relatively basic one, but you should be able to at least explain to me what's going on, where's what, label those vectors, and as I said, if you're gonna have a sheet that's gonna allow you to be able to have a sample of that on there, you should be able to take from that sample and approximate that system. There's a reason why I was thinking about it beforehand, that I know I don't wanna put this into a circumstance where I'm incentivizing you entirely to worry about memorization. I would prefer you still focus on conceptual learning, and I think that if I push too much away from being able to have a note sheet so that you feel comfortable with that you have the knowledge on the structured things, the memorization things, it'll make it easier to remember those characteristics, okay? How much time do we have left? About a half hour, okay. Error minimization is done through what? Iterative parameter estimation. I run the system forward, right, through some form of initialization. Relative to the complexity of the network, I'm going to have a number of computations I have to make, inputs times weights, passed off between layers, bucket chain, passing off, okay? Forward pass process is going to be deterministic. Everybody with me there?
Yeah.
But what's the relationship of why one network is different from another? Because the initialization is randomized as well. So the weights that make up the network, two networks can have an entirely different set of outputs for their first run and can end up in entirely different places with regard to the accuracy of the output, because one network could start at a really good place relative to the gradient. It could just get lucky on its dice roll, right? Whereas another one could start off in a very bad place. What typically tends to happen with these networks, the closer they are to the correct solution, they actually tend usually to learn a little slower, okay? Because there's not a lot of additional progress to be made very quickly. If it has a lot of error and there's a lot to correct, right, the system's gonna see pretty big gradients and it's gonna backprop those large gradients a little bit quicker. What's gonna happen to those two networks? Ultimately, they're gonna kind of, even though they're starting from two different places, they're ultimately gonna end up kind of in the same spot along some chain of the process. They're relatively going to converge to somewhat the same space. If we utilize some of the other techniques that we talked about to discourage some of the bad behavior that we saw within the network, we're going to get an improvement in that operation. So perimeter estimation is that relationship of the iterative update of those weighted parameters. Now this applies to both the convolutional neural network and the fully connected network, in the effect of saying that the array, which we call a kernel in the CNN, is in fact a series of weighted elements. It gets a little bit of a different process of how we backprop the values into the kernels, right? But we still know that we're still updating those kernels based upon trying to drive down the overarching total error within the system. We're trying to get those kernels to find features that we can use to be able to classify, right? Ultimately, that means that kernel has an error in it, and we're gonna have to try to figure out how to make that kernel better. But that means that we might have, if it's a 3x3 kernel, we have what? Now 9 values that need to be adjusted in order to be able to try to figure out how to make that kernel act better and contribute better to providing us with reasonable outputs for the classes of interest. Okay, I'm focusing mostly on classification with the discussion for CNNs. Fully connected layers, we didn't do a lot with anything else. We talked a little bit about regression, right? Mainly about the idea of using MSE to determine estimation. And that's really not a lot different than we might encounter in any other polynomial regression framework, right? It's just actually, in some senses, I feel like using a neural network for regression, what do you have to do about it? You have to be very careful, all right? It must be an adequately complex function for you to apply a neural network to it. Because if it's something that's just really pretty much a normal function, or like an offset of a sinusoid, or just a first or second order component, fit that, okay? Don't go to a neural network. It's too much. It's that nuclear weapon to swat an at, okay? Big hammer, everything looks like a nail. Remember that part of the definition of understanding how to utilize machine learning is understanding enough about the problem to determine whether or not there is adequate necessity with respect to the underlying complexity of the problem to merit the application of something so aggressive with respect to its capacity to fit to the space. Neural networks are very, very liquid, okay? The term I use is that they fit to the shape of the container. If the data is the container, you pour the network in there and it just takes on the shape of that data. Such to the point to where many networks, you can do what with them? You can actually get them to reproduce their outputs if you run them backwards. That's how much they effectively become a representation of the data that they're actually trained on. So the network itself, once it converges and once the parameters are optimized to it, its characteristics are as much a part of or a reflection of the data it was trained with as they are a reflection of the understanding of how that data correlates to some phenomena, right? The map between inputs and outputs of the model space. The gradient descent process, I'm going to review this in much more robust fashion, okay? And that'll be a video. I'll stay up tonight as late as I need to finish it, okay? That's going to have some new slides in it, all right, over the ones that we had in are just general lectures, because you can go back and watch those if you want to see what I did before. But I figure the review probably earns us looking at some other slides. So I put together some slides for us, walk through that. I'm also going to have the universal approximator slides, do the visual version of that for you as well, just to give you a baseline there. Error estimation utilizing the loss function system is that mechanism by which we adjust based upon the gradient estimation. We go in the opposite direction of the gradient, which itself is a surface that is tangent to the error space that indicates the instantaneous value of change in the function of error, right, from one position to the next, jittering around a tiny space. We get a vector normal to that surface, and that vector has both magnitude and direction to tell us the value and adjustment, positive or negative, to that particular weight in order. The gradient does this. It tells us the maximization of a function, right? Gradient returns max. So since gradient returns max, if error or loss is the thing that we're interested in, right? This is actually a really weird trick. Remember we talked about this, but it's a weird trick because we automatically assume that if we know the direction of maximum increase, that if we just go the opposite direction, we should be going in the direction of maximum decrease. It's not always 100% true, but it's close enough that if we do it over and over again, we can eventually converge to something realistic, right? So you keep going what seems to be immediately downhill from wherever you are by taking the negative of the gradient away from the weight, right? Current weight minus the learning rate times the gradient estimate at the local position, will be the mechanism which we describe as stochastic gradient descent, right? We're taking into consideration a constant update process. We will talk about a slightly more comprehensive methodology that we use. We call the quasi-Newtonian methodology, and it takes into consideration the second order derivative characteristics of the error surface. But what I'm going to tell you right now is focus on the SGD methodology and the understandings of how we can apply some of the additional characteristics for that descent mechanism, such as how Adam utilizes momentum, right? As well as utilizing some decay functionality, right? Regularization. We talked about both of those ideas as well. All right, so we use this least mean squares error surface estimation, learning rate optimization, and then scheduling methodologies as well, right? So we can schedule a decrement in the learning rate just depending on how long the model has been running as well. So early methodologies, before people started thinking about the idea of effectively taking the inertia of the gradient and utilizing that as part of the system, right? Watching the ball roll downhill, people just said, well, we should be getting closer, right? The immediate solution is that after a certain number of times we do it, we've moved from somewhere higher to somewhere lower. So that means what? Slow down, right? Slow down. And so we can just decrement based upon some number of epochs, some number of periods, right? We say every 10 intervals, right, of the training process, just go ahead and reduce it, okay? You reduce it by 1, reduce it by half, you can reduce it to 10%, okay, whatever it is. That doesn't necessarily solve anything when it comes to getting stuck at local minima, right? So that was a big problem that we incurred, we talked about as well. So local minima and global minima are a consideration there, right? What's the global minima? Woohoo, party time, we got there. We got the best solution that's going to exist with respect to that particular feature characteristic within the multiverse. We know it exists. Here's a weird consideration. We know a global minima exists. We will probably never know that we got there. We may have found it and we will never know for sure that we arrived at it. Why? Because we can't know that there isn't another space that is better. So since we know that we're always going to have non-zero error, right? And that we only see zero error when what happens? Overfitting, right? So even if we hit the global minima of a system, we really aren't going to know whether there's a way to improve it or not unless we search for every single possible configuration of parameters. What was the one thing that we were trying to avoid by using this methodology? Exactly that problem, okay? So we're going to get the best we can come up with. This is one of the things that's problematic with regard to this topic in general, is that those of you who are, once again, I state this, those of you who are very tied up in this notion of got to get the right answer, okay, you're going to have to relax it. You're going to have to relax it to saying that it's always going to be effectively good enough, right? Or the best we can do within the time allotted before we just have to stop because things don't appear to be getting any better from where we're at. Most of the time, we can do that relatively quickly by taking a comparison, something like test train splits, right? So validation early stopping mechanisms is one of the methodologies also by which we can stop before we go too far into the overfitting space. Gauss's theorem is actually related to something that I'm going to talk about in the full update. I want to put that in the context of activation function saturation. I'm going to show you some visualized examples of that because we didn't spend a lot of time on it, but I just want you to know what it is, okay? And it needs to be in the context of this space because it's not really apply elsewhere. That might be an extra credit question or something, okay? Blame game extra credit, or excuse me, extra credit. The credit assignment problem, right? Who owns what with regard to the total error of the system in the backdrop? Loss and error approximation methodology. How do we appropriately determine the ownership of the weight with respect to the error? We're going to have to incorporate that the error component, the first level of error that's incorporated with the error component is due to what? The partial of the activation function. How correct the activation function is for the appropriate task is a partial component of the total error of the system. So the first partial of the system and the back prop is the activation function. The next partial component, right, the product thereof is going to be the weights of the layer component, right? And those weights are fed into by what? The activation at the previous layer. So we can chain, we use the chain rule of calculus to treat the likelihood of the correct values being propagated through the system as effectively a chain probability relationship. Right, so we know that there is a chain of probabilistic relationships of the correct value being selected. Then we also know that we can chain back the partial derivatives of each of those weights. And as long as we apply the derivative characteristic of each of the functions in stepwise fashion to the previous elements, we can construct a matrix that allows us to adequately prescribe ownership of the blame, right? We spread the blame around. That particular focus and emphasis on this in this class is one of those things I say, I repeat it over and over again, because at some point in time, if you get it, the remainder of all the rest of this stuff clicks into place, right? It's the shower knob problem. Remember we had the shower main and all that stuff? It's the shower knob problem whenever there is a wall full of knobs, okay? The system humans would employ would be go and fix one dial at a time and try to see how it affects the system in the end. The backpropagation methodology, utilizing the chain rule and being able to backpropagate through the partial derivatives of the activation and the integration functions, right, allow us to know what amounts of the local gradients we can utilize to update the final error, right? So if we minimize the relative instantaneous gradient for each function by taking the exact opposite of the localized computed gradient for that particular weight relative to the total error in the system, we can adjust all the dials at once, and we're actually minimizing in multivariate and multidimensional space simultaneously. We're even accounting for some of the covariate factors involved within the system, such that some things will vary with respect to other things. That adjustment parameter, right, that update system does not have to be perfect, and it does not have to capture all of the error. Matter of fact, we know that it is not ideal for it to capture all of the error in one single step, right? You shouldn't take all that you think that weight is responsible for and crank that knob all the way over, because we do not know what that error function looks like very far at all in advance of immediately where we are, okay? The whole world is fog except for that area in which we are standing on. That gradient surface could take crazy dips in a relatively short period of time afterwards, or could have a crazy spike on the other edge of it. So if we overemphasize knowing what's in the future for us based upon what we see instantaneously, right, we'll get overconfident and try to capture too much of the understanding of the space at once. That's the reason why we use small and intentional iterative processes in order to update the weight system, okay? Why would we implement weight decay? I put a little star up there behind it. It's something that we also need to talk about. What did we talk about that weight decay did?
L1 and L2 regularization.
It's a type of regularization, okay? We can employ either L1 or L2, or we can apply elastic net, which is a combination of L1 and L2. Okay, I don't expect you to remember that formula because it's a little wonky, but L1 and L2 regularization should be fairly straightforward to you, right? One is fairly aggressive, right? And two is slows a little bit more as it approaches a zero value, right? So L2 regularization utilizes a square component. The 2 indicates the square. That square component indicates that as the value goes below 1, what happens? It slows. The process gets slower and slower. What happens as the value of a weight effectively goes towards 0 with respect to most of our activation functions? What happens to the gradient of the error surface for it? It flattens out. It goes to 0, right? That weight dies. Okay, it dies. So L1 is aggressive because it pushes many things and dies, right? We talked about the idea of we could utilize that to take advantage of creating sparsity within the network by cutting out the connections we don't need, okay? A sparse network runs faster and may actually improve the total performance of the system by eliminating unnecessary features and unnecessary combination processes. It also may stop the network from overfitting, right? Because removing and reducing the number of perimeters within the network can be an effective way of stopping it from memorizing. Because if it doesn't have enough memory to be able to adequately store the patterns of the samples within the matrix of that system of interconnections, then it won't be able to effectively memorize. So ablating, covering up, dropping out can be an effective process. All right, we already talked about probability, we talked about entropy, predictive power, we just talked about regularization and overfitting control. Noising, all right, we talked about this a little bit, about the idea that adding noise to the data can be another methodology by which we can attempt to stop overfitting. How does that work? Because if every sample looks slightly different because it's got a slightly different set of noise over top of it, because noise in itself is random, then that means that random elements of that sample are going to get changed around a little bit. It's going to be harder and harder to memorize a sample about basic positional elements whenever we know that there is a recombination of the characteristics for that particular space. So the noising also helps the system become more robust in additional conditions, primarily because of the fact that it simulates what could happen under bad conditions, worst case scenarios, right? So add relatively high noising levels to the samples you're training the system with, and what will happen? It will learn how to detect the elements of interest and separate those elements of interest from the signal from the noise, right? The signal is the portion we want from the noise processing. So that actually implies another interesting relationship, which we already know about the notion of the weight matrices and the effect that the weight matrices are filters. The transformations that are actually happening within this space are both spatial transformations as well as frequency-driven transformations that can accomplish noise removal or noise reduction. So if we give it a noisy sample and we make it have to denoise the sample, if it gets a clear one later, it's going to say, easy, no big deal, all signal, no noise, right? You give it a noisy one because you have some bad input at some point in time, and at least it'll be able to handle working under those conditions. Anybody ever taken a picture in low light? Anybody ever zoom in on a picture in low light? What do you notice about it?
No, too much noisy.
They're very noisy. What's one of the main reasons behind that? Anybody know?
Because there are less photons and lights in there due to that reason. And
Okay, you're exactly right. That's the first part of the process, is that the aperture has to be left open a little bit longer in order to capture enough light. The second reason behind it is an interesting one, and that is amplification. So since we're only getting a small amount of light, we have to boost the level of the signal in order to be able to get something we can visually see. This is actually related to that normalization concept, right? We're getting it up to a level that makes a sense to us in order to be able to differentiate even low intensity pixels from one another. Imagine trying to take a picture of a number in low light conditions and getting the system to identify the number. You'd want to add some noise to the training sample data so that that model would work when taking a picture of it in low light conditions. So that's an example of how a real world application of noising as a methodology of data augmentation is a mechanism by which we can make the model more robust to application performance in the future, as well as to avoid overfitting characteristics and to imply that the characteristics of the filtering capacity of the system are present, right? Separability in systems ultimately relates to the dimensionality projection capacity. That's a classification method, right? We just talked about augmentation. What other augmentation methodologies did we discuss? We haven't employed them yet, but we talked about a few of them. They're pretty straightforward and simple. You guys remember what they were?
Rotating the image.
Rotate it, right? Flip it
Zoom in.
around, right? And then randomly crop it.
Yeah.
Those are the ones we usually utilize most frequently, all right? We also can do stuff like distortions and reprojections. But those are, you gotta be a little careful with those because they can distort some of the feature characteristics in the system. So as long as they're not extreme, right? I'm more looking for the basic concept behind this and the effect of saying that it's kind of a methodology of simulating what might happen if we collected new data from the space. And that in and of itself allows us to be able to produce more samples, right? And with more samples, we can do what? We can stop the system from effectively memorizing any given one of them, right? Recenter what's going on in the space, rotate it a little bit, and what do we also allow the system to learn to do? We allow it to learn to be rotationally and scale invariant, right? We note that the process of convolution networks, especially the idea of pooling layers, allow us to be able to avoid that initial process issue, okay? Data division, you guys have done a little bit of this. Some of you guys have chosen validation-based stopping. We talk about how we label data and indexing. Everybody knows this one's pretty simple. What the concept of test holdouts and what they're for, right? These are gimme questions in a sense, because as long you should be able to answer these as the same question answers that you get in every data science class, right? Why do you need testing? Because you've got to check and make sure that it's a model that will work in the future. If you don't have the ability to go and pull new data for it, you need to hold some back just to be able to check and make sure it's working. Okay, we've already talked about all of that. Okay, yeah, we already talked about all of that. Some of this is repetition in a sense, just an expansion on it. Memorization, computational complexity. Oh, this one needs to be discussed. I have two right there. I'll fix that because that's going to go in with the Gaussian. So that one will probably be the one I actually put in for extra credit, okay? Learning rate schedules, inertia methodologies.
So
We
which
talked about edges, structures, methodologies, abstractions, feature extraction processes. We started off talking about that. Yes, Sean?
So which one you told us like extra credit like?
Okay, if you don't recognize it because we haven't talked about it, it's probably extra credit, Sean.
Okay.
Okay, good. It was talking about the idea of XOR decision surfaces, okay? XOR is the example of that specific decision surface. The exclusive OR operator creates a real problem in the effect that it cannot be approximated by a single layer perceptron, whereas the AND or the OR functions are easily approximatable with a singular surface operation. So we utilize the XOR operation to represent the dimensionality of recombination of surfaces for a multi-layer perceptron. So you actually need more than one layer to approximate the XOR function. It's just it's a classic example of the idea of the universal approximator as a piecewise integrator of linear functions, right, and non-linearities. So you can actually create smooth transitions that create strange shapes throughout the decision surface by recombining relatively straightforward activation functions, right? Sigmoidal nonlinearities can be turned into smooth curvature operations by adding their outputs to one another in order to be able to create the center of the XOR to be ones while the outside are zeros, right? I'll talk about that in the video. I already have that part actually done and recorded. So spatial preservation, structural preservation, frequency-based characteristics of feature extraction, right? How do we get the features? What are we looking for? What's the idea of putting abstraction together to create and to propagate forward values? Be able to identify the major types of layers that we have, okay? I'll probably use Kiros's syntax. It'll be super straightforward, like you'll look at it and say, conv 2D, right? You'd be like, that's 2D convolution. Pool 2, that's a 2-point pool. The thing that I'm telling you is some of this stuff is like so self-evident by itself that I'm having difficulty figuring out exactly how I'm going to ask the question without it giving away the answer. Okay? But that's good. You guys like that, don't you? Okay, that's fine. Okay, so as long as you can read, some of these stuff will be easy. You will need to do a little bit of math with this, okay? But the math that you have to do with that is really easy, right? Because what happens whenever a kernel of a certain size is taken into consideration, it cuts off some of the edge, all right? How much does it cut off? It cuts off rounded down from half of the size of the space, right? So if it's 3 kernel, right, it cuts 1 off going in and 1 off going out. So you're going to reduce the dimensionality of the input based upon the size of the kernel. So we're actually just gonna calculate the basic process, similar to what you guys did on your homework or your project, right? That calculation of a small little network, be able to tell me what the dimensionality was. And you might want to bring a calculator, okay? I'll tell you this, I might actually ask you to tell me the number of parameters in those layers, okay? So I'll try to bring some extras, but I may not. That might be just busy work, but be prepared to at least recognize and do some mental math with the layers. We've already talked about it. Okay, we're done. We did good. Everybody happy? Anybody else want to ask anything else? Any questions on anything we talked about there? Anybody ever seen that meme that's like, you know, you go into class and it's like the teacher's drawing on the board 2 + 2 = 4, and then you get into the test and it's like, Jimmy has 2 apples and Sarah has 1 apple. Calculate the mass of the sun. So expect questions like that, okay? No, I mean not those questions. Expect to think a little bit on some of it, all right? But most of it, just expect to be able to discuss the concepts, retain the information, and make some reasonable inferences about what's going on, okay? If you know how backprop works and you basically understand the concept of kernel convolution, we should be good to go, okay? The rest of it's practical. That's the nice part. But that means we have to start doing some stuff once we get it done. All right, I'll see you guys on Tuesday. Thank you very much. Good luck in your preparations. I will see you before then, but I will see you, but no, you will see me, I won't see you. Be patient.
Wait, what?
What's that? Talk back on these people.
No, I was writing everything you said. This is all you said, that's it?
Yeah, let's just,
How much? You're typing fast.
what works?
I know.
Is it free, like,
Damn.
Let's try like,
I'm also a gamer, but I'm not that fast. I type.
Dude, this keyboard actually makes me really slow. Like, I feel like I can't type very fast on it. I'm gonna bring in my cherry red.
you know what, I'm gonna, why don't we just go ahead and go for like,
I have one of those at 11 o'clock. And everyone's like,
11 o'clock, and send me make a pad.
I will be ready.
yeah. And like, so like I'll be around the dogs.
Hey, if you're,
Yeah, Sunday.
There's a flight to
Yeah, let's do it on Sunday. I'll be busy.
not next week. Yeah, I just told you, go ahead, Kim, so I'm just gonna be talking about that problem.
Yeah, I figured last time you were gonna do the playground website.
No, I did the universal approximate. Yeah. You guys haven't seen it. See you. See you.
Yeah, so watch that.
Probably shoot you an email.
I'm gonna see. Traffic's. Yeah.